Hey everyone, this is section 2.4, more on slope, and let's go ahead and let's look at parallel lines. So now I have two parallel lines here, and we can tell they're parallel visually, it looks like it. Let's see what it means in terms of algebra to be parallel. I'm going to take the purple line right here, and I'm going to count off its slope. So I'm going to start right here, I'm going to see how much it increases to about right here. That's the next time it hits another grid line, so it's going to go up 1, 2. So it's going to go up 2 spots there. And then I'm going to see how far it goes over, and it's going to go over 1 spot. So it's got a rise of 4, and switch to purple. So the slope for here is 2 over 1, or just 2. Now let's do that again with the black line, and let's see what its slope does. So it starts off at the origin, and here's a grid line, so it goes up 1, 2 right here again, right? That's 2. And it's going to go over to here to that grid line, over 1. So for this red line, the slope is 2 over 1 again. It's 2. So what do we know about these parallel lines? They have the same slope. And that's the big key with parallel lines, is that they have the same slope. So we could say that two lines are parallel if they have the same slope and different intercepts. So what's our big equation of a line? Y is equal to mx plus b, right? So it's going to be the b that's different. And then m would be the same. So if I have y is equal to 3x minus 1, you know it would be parallel. Y is equal to 3x plus anything but a negative 1, so plus 7. Then that's a parallel line. So if I need to determine a parallel line, determine the slope, change the intercept, get a parallel line. Great. Let's talk about perpendicular lines. So I've got two lines right here, they're perpendicular, and we can determine perpendicular again by looking at the slope. So let's take this blue line and let's count off its slope. I'm going to start right here at 0, 1, and it crosses again out right here. We'll go to that intersection at 3, 0. So the slope, and I'm going to do it this time with points, is, let's see here, it starts at 1 and it ends up at 0. So 0 minus 1 divided by ends at 3, starts at 1, 3 minus, it starts at 0, pardon me. This is 0, 1, and then this is 3, 0. Okay, so that's negative 1 over 3. So that slope is negative 1/3. That's the slope for our blue line, our first slope right there. Now let's go ahead and let's do that with the red line. I'm going to start right here again at 3, 0. And then I'm going to end up right here. This is where it crosses again. So it crosses again over here at 4, 3. So I can compute that slope, m2, by doing 3 minus 0 over 4 minus 3, and that's 3 over 1, or just simply a slope of 3. Ooh, interesting. This is different. Let's take a look at these two slopes And what we do is we take and we multiply them together, and we get negative 1/3 times a positive 3. That gets us negative 1. And the relationship right here, this relationship is called the negative reciprocal. So they have a negative reciprocal relationship. That is to say, they multiply to give us negative 1. And if that's the case, then we have perpendicular lines. Negative reciprocal slope means the product is 1. And we can check by multiplying. So let's say I've got a line 2x minus 3y is equal to 4, and I want to find a perpendicular. And that little inverse t thing means perpendicular, because it makes a little right angle. Then I'm going to determine slope. 4 minus 2x, or minus 2x plus 4. There we go. So y is 2/3 x minus 4/3. Determine the slope. We get negative 1 over the slope. We get the negative reciprocal, which in this case for 2/3 is negative 3/2. And that would mean our other y, actually let's not call this y, let's call it f of x now, would be negative 3/2 x plus pretty much anything. It can even be that same negative 4/3. We'll just put plus 2 in there. And then that's a line perpendicular to our given line. Let's talk about slope as rate of change. Slope is the rise over run of a graph, right? It's the rise over run of a function. So if I'm looking at this, I can look at the slope of this, and I could say that with every change, I change 1 in x, change 1 in x, y is going to change 2. I go to the right 1, means that I need to go up 2. If I have it for this one, I go to the right 1, I need to go up 3. So that rate of change is 3:1 versus 2:1. Slope is rate of change. So if I'm looking at a line right here, I could look at this green line right here. This could be a curve describing some sort of function, some sort of like height or population growth or something that I'm interested in. And this purple line goes from the same endpoints, right? It goes from the same endpoints. Starts here in the same place and then intersects over here in the same place. So its rise and its run is the same. It rises 1, 2, well, let's use, numbers. So it goes 6, 6, and this is negative 6, 0. So the rate of change for this purple line is 6 minus 0 over 6 minus a negative 6, which is 6 over 12, or 1/2. So that means the average rate of change for that green line is also 1/2. What about, say, right here, from negative 6 to this, from negative 6, 0 to, what is this, negative 3, 3, the average is 3 minus 0 divided by negative 3 minus a negative 6. So that's 3 over 3. So the average rate of change is 1, or the average slope from this point to this point, the slope of this teal line is 1. This has m equals 1. So we could take an average rate of change by looking at just part of a line, part of our time, and comparing it to the whole thing. Like, for instance, let's call this right here the point 0, 3.5. Then that average would be 3.5 minus 0 divided by 0 minus a negative 6, which is 3.5 over 6. I think we'll just leave it like that. And that would be the rate of change from this starting point to this end point. And we could also take it from different starting points as well. I could compute an average rate of change from negative 3, 3 over here to negative 6, 6. And that would be, call it the average slope of 6 minus 3 over 6 minus a negative 3, 3 over 9, 1/3. That's the average rate of change in this region. So we need a region, and then we need a function. Then we can compute our average rate of change. Alright, that's it for this video. I'll see you next time where we will work some exercises.